Hello everyone, this is Rajat from IIT Bombay, and today we will discuss question 15 of GATE 2020 for our discussion. Here C3b point is given along with a reducible representation of pyramidal AB3 group. We have to find out the normal Raman active mode for the same molecule. Now to understand this question, we have to know some concept of character tables, irreducible representation and reducible representation, and then we can, in the last part, we can easily solve this problem. Now each and every character table is designated to a specific point group because each and every point group has some specific symmetry classes, and depending on that the number of rows and columns will be fixed for a character table. These values that are there are known as characters. We will know regarding them in the upcoming slides. Each row is known as the representation, specifically irreducible representation, and they are named as Mulliken symbols, A1, A2, E, there are B1, B2, and so on. Last two columns represents Cartesian coordinates and rotations for this one and the quadratic terms that are there respectively. Now a representation is nothing but a set of matrices which represent a symmetry operation, and they can be combined the same way a symmetry operator can be done. Let's check how this matrix can be generated using a simple symmetry operation E. When E is applied to something, it will produce the same thing. When if it's a one-dimensional thing, let's say X, E into X will produce X itself. So E itself can be represented with a matrix of 1D, 1 cross 1 matrix containing 1. If it's a two-dimensional thing, it can be represented by a 2 cross 2 matrix, a diagonal elements are 1 and off diagonal elements are 0. In 3 cross 3 scenario, the case will be same, diagonal elements are 1 and off diagonal elements are 0. Now let's imagine a element which has more number of dimensions or more number of components. Then the size of the matrix will be very big, and that's why we can't write those big matrices in a table to represent the characters of that table. And that's why what we have to focus on is, instead of going through whole matrix, we'll focus on the sum of the diagonals. It is known as the character of a matrix, and write all those values into the character table itself. Now a irreducible representation is nothing but a representation that cannot be written as a combination of other representations. To check which can be something like that, let's go with a simple molecule of H2O, which has a Z direction in this direction. We know H2O is has C2b point group, so except E, the other elements that are there, symmetry elements, C2, sigma xz and sigma yz. Now let's check a specific X vector and apply all those operations on them. We'll get, when we apply C2z on X vector, it will change its direction to -x. When we apply sigma xz, it will change direction from sigma. It will not change direction of X. It will remain the same. Sigma xg on X will produce X itself. If we apply sigma yz on X, it will again change the direction because it is perpendicular to it. So if we write the matrices for them respectively, E matrix, as it not changing X, will produce 1 cross 1 matrix. C2z, as is changing the sign, it will produce a 1 cross 1 matrix containing a value of -1. The same case will be for sigma yz, and so the character table will look something like this. Now the representations that are there that can be written as a combination of other representations, quoted irreducible representations, those are known as the reducible representation. An example for that will be, let's say we go with the H2O molecule again, and we'll now count the unmoved bonds that are there when we apply some symmetry operations. When we apply E, the identity matrix or identity element, there will be no change. So if there are two bonds, the number of unmoved bonds after application of E will be also 2. Let's apply C2 itself. C2 will rotate this and shift this hydrogen to there and this hydrogen to here. So the bond will shifted. No, there will be no unmoved bond, so that will be 0. For sigma xz, There will be no change because sigma xg has the same plane as the molecule itself. So there will be no exchange of bonds, shift of bonds will get two unmoved bond. And if we go to the last one, sigma yz, again this hydrogen will be shifted there and it will be shifted in this side, and number of unmoved bond will be 0. So the representation that will be there will be something like this, 2020. Now, if we check the character table of C2V, it will show that there is no such irreducible representation that is looks like something like this. So this is a reducible representation, and it can be written as a combination of two or more irreducible representation. In this situation, tau will be A1 plus B1, and that's a very easy. We can just add all those values. We can produce this thing, but it will be not that easy for other character tables, and that's why we need a formula of how reducible representation can be written as a combination of other irreducible representation. For that, we will use this formula, where AI is nothing but the number of times one irreducible representation will appear in some reducible representation. H is the order, N is the number of elements in the corresponding symmetry class. For example, in this C2Z symmetry class, there is only one element, that is C2Z. But there will be a situation in our problem itself where in one symmetry class there will be more number of elements. XR or Xi-R, as you will see it, and Xi-R are the character of reducible and irreducible representations that are there for a symmetry class. Now let's use that formula for our case. We have to first know the order of this group. C3V, as we know, the CNB point group has the order of 2n. So C3V will be having a point order of 6. Keeping that in mind, let's use the formula and first check how many times A1 will appear in this tau reducible representation. 1 by H, H will be replaced by 6. Now we have to first start with E. Let's number of symmetry elements in E symmetry class is 1, only one identity, so 1 will be there, into Xi-Ir, that's the character of irreducible representation, is 1, so we'll replace 1 here, and then we place the character of reducible representation for E, that is 12. We'll follow the same thing, as there's a summation sign, we'll follow the same thing for other symmetry classes also. For second symmetry class, the C3, we can see there is a number 2, there is 2 number of symmetry elements in C3, that is C3 and C3-1, something like that, so that's why 2 is there. So 2 will be there, then Xi-Ir, that is 1, followed by Xi-R, that is 0. So, and similarly for the last one, symmetry elements in this symmetry class is 3, so 3 followed by Xi-Ir, the character of the irreducible representation, 1 followed by the character of the reducible representation, 2. And if we sum it up and do the mathematics, we find out that the A1 comes out to be 3. You can do the same and find out the number of times A2 and E appear in the reducible representation tau. So tau can be written as 3A1 plus A2 plus 4E. Now this tau is nothing but a combination of translational, rotational and vibrational modes, and this vibrational modes has a knowledge of that Raman modes itself. So we have to first find out what is the vibrational mode that is there. To find out that, we need to know what are the translational and rotational modes are there, and that's where these two columns will come handy. To find the translational mode, we have to check for x, y, z in this character table, and can check easily see that z is in the z has a contribution from A1 and xy has a contribution from E. So tau translational will be a combination of both of them, A1 plus E. Similarly, for tau rotational, we have to check for Rx, Ry and Rz in the character table. You can see Rz is here, so rotational has a contribution from A2 as long as with from E, as there is Rx and Ry. Tau rotational will be A2 plus E. Now just do the basic algebra to find out vibrational states, and we found out that it has become 2A1 plus 2E. Now Raman vibrational mode itself has two contributions. One is from IR mode and Raman modes. IR modes can be checked or can be designated via its relation to the dipole moment, and dipole moment are related to distance. So all the Cartesian coordinates that are there, they are representing the IR modes. Similarly, if you check Raman spectroscopy is related to polarizability, which has a unit of Faraday into meter square. That means the square terms of coordinates, that is the quadratic terms x square, y square, xy, xz, yz, they are the representing factors for Raman spectroscopy or Raman modes. If we check the point group itself, we can see those values are here and here. So A1 and E both are representing the Raman modes. If we see tau vibrational, it has both the contribution, and that's why we can write that tau Raman is 2A1 plus 2E. So from the answers that are there, the options that are there, you can see the only answer that is suitable for us is option D, and that will be our answer for this question. Now, for this specific question, if we see the other options from them also, without any kind of calculation of vibrational mode itself, we can easily say what is the active Raman mode will be. We can just check that the quadratic terms are A1 at A1 and E. So the Raman and the answer that is there also should contain A1 and E both and not A2. And if we check A and C both contains A2, so they are not right. In B, there is no A1, so that will also be not right. So the only option that is remaining, that is D. So in this way also, taking a short path, we can answer the question. If you want to understand more about the group theory and specifically for reducible and irreducible representations, you can check the videos that is there in the YouTube for NPTEL courses by Professor Aninda Datta, and it is the link for that. That's all from my side for this question. Thank you.